Welcome to solverfy.
We know here we can look at the data from figure 3037b, and we know that at t equals 0, rather we can say at t equaling 0, we have a current 0.0015 amperes equaling the voltage of the battery divided by R, the resistance. So we can then say that the resistance would then simply be equal to the voltage of the battery, 6.00 microvolts, divided by 0.0015 amperes. We find a resistance of 0.0040 ohms, denoted by capital omega. We can say that now the value of the current during 10 seconds to 20 seconds, so during that time interval, we find that we can say that the voltage of the battery plus the induced EMF divided by the resistance, this is equaling 0.00050 amperes. And so we can then calculate the induced EMF using our newly found resistance and the existing voltage of the battery. So we find that the EMF is going to be negative 4.0 microvolts. And at this point, we can use Faraday's law. So at this point, we can then say that the EMF is going to be equal to the negative change in magnetic flux with respect to time. This would be equal to negative A times the change in the magnetic field with respect to time. This would be equal to negative A times A. And so essentially, we can then find A. A would be equal to the EMF divided by, rather we can say negative EMF divided by A, and this is going to equal to positive 4.0 times 10 to the negative 6 volts divided by the area of 5.0 times 10 to the negative 4th meters squared, and we find that A is equaling 0.0080 Teslas per second. This is our final answer. That is the end of the solution. Thank you for watching.